Hello, Sir Farid. In this video, I will be presenting the I-beam strain measurement analysis. So here is the table of content, and in this presentation, we will directly proceed to the experiment parameters and analysis. So the first topic is experimental measurement. As shown in the table here, the measurement were conducted on the I-beam with corresponding parameter. Another measurement was taken to determine the strain gauge position from the lowest part of the beam. And now the data result. As shown in the figure displayed on the slide, there are two graphs. The left graph shows the I-beam strain measurement result at corresponding time increment. This graph contains 7 plots. Each plot represents the strain measurement result for strain gauge A, B, C, and D, which is the uniaxial strain gauge, and gauge E, F, and G, which is the triaxial strain gauge. Strain gauge A shows a negative strain value while B shows a positive strain value. This occurs due to the direction of the applied load, since the load is applied upward. Strain gauge A experiences compression while strain gauge B experiences tension. This indicates that the strain gauge accurately represents the strain quantity at the respective position. The other uniaxial strain gauge exhibits similar behavior with strain values corresponding to their position on the beam. Uniaxial strain gauge A and B reveal normal strain, while strain gauge C and D record both normal and shear strain based on the position. On the other hand, the triaxial strain gauge, which consists of three uniaxial strain gauge, primarily measures shear strain. This is because at the center of the beam, no normal strain occurs, but maximum shear strain is present. Thus, triaxial strain gauge are required to measure the strain in the shearing direction. And the plot on the left, at the plot on the right, demonstrate strain behavior under incremental loading, showing similar trend to the strain versus time graph, and it illustrates how loading condition cause strain values to vary at specific beam position. And to determine the mechanical properties of the I-beam, the first calculation is the area moment of inertia. The area moment of inertia is crucial in mechanical and structural engineering as it quantifies a structure's stiffness against bending, with larger values indicating greater resistance to bending. It also plays a vital role in determining how stress is distributed within a cross-section under various loads. Additionally, it aids in optimizing the design of the beam, shaft, and other component by minimizing material use while ensuring strength and stability. Furthermore, the area moment of inertia influences natural frequencies and dynamic response of component, making it essential for vibration analysis and performance evaluation. So here is the result of the calculation of the area moment of inertia of the I-beam strain that we calculated. And the next calculation is for the section modulus. The section modulus is a measure of the beam's capacity to resist bending moment, and a higher section modulus indicate better bending strength. It is used in beam design to ensure the material's maximum allowable stress is not exceeded under loading condition. This helps engineer design efficient, safe, and cost-effective structure while preventing failure due to bending stress. As shown in the relationship here, the relation with tensile strength, uh, we can observe how the variation in the section modulus affect the strength of a material. And here are the calculation and the corresponding the yield result of the section modulus. And because we are dealing with shear strain too, it is also important to understand the distribution of load, shearing force, and bending moment throughout the beam. And this is depicted in the diagram displayed. From the shear force diagram and bending moment diagram, we can determine the corresponding shear force, load, and bending moment at particular position of interest. And in this case, the SG, meaning the location of the strain gauge position in the beam, and with the corresponding. And the next one is about the calculation for Young's modulus and shear modulus. These calculations are derived from all the relevant parameters to define Young's modulus and shear modulus with the result shown here. So for the Young's modulus from the experimental data, we obtain the result of 65.41 GPa. And for the shear modulus, we obtain 27.56 GPa. And in this slide, we show the comparison between the theoretical value found in reference and the experimental value obtained from the experiment. And there is also a small error between the theoretical and experimental value. So the error for the modulus of elasticity or Young's modulus is only 3.81%, and for the shear modulus is only 10.24%. Because, yeah. And in this slide, we compare the theoretical strain value calculated using the derived strain formula and the experimental strain value obtained from the experiment for each uniaxial strain gauge, which is A, B, C, and D. And the results show a small error between the theoretical and experimental value, and the small error is due to the minimal difference in the mechanical properties value that we already calculated in the previous slide, which is the which is the elastic modulus. And for conclusion, we analyzed the strain measurement on the I-beam using both uniaxial and triaxial strain gauges, and the experimental result demonstrated that the strain value recorded aligned with the expected behavior based on the applied load and strain gauge position, effectively capturing both normal and shear strain. The calculation of the area, moment of inertia, and section modulus highlighted the I-beam structural stiffness and bending strength, which are critical for assessing its mechanical properties. Additionally, the comparison between theoretical and experimental value for Young's modulus, shear modulus, and strain values revealed minimal error, confirming the reliability of the experimental method and calculation. And understanding this parameter is essential for optimizing beam design, ensuring structural integrity, and improving load distribution in practical engineering application. This study reinforced the importance of accurate strain measurement and mechanical properties analysis in structural engineering. So here are the references, and thank you.